All right. So what we're going to be covering today is basically the Pendulum Lab that we went over last class. If you were absent, I'm going to give you sample data. It will be the data in this table as you guys see. So if you're watching and you were absent, or if you guys are in class and you were absent, my recommendation would be grab a piece of paper and try to follow along because the math will be the same. If you have your own data, right, you're going to have a different type of mass, a different level from the ceiling to the mass, a different measurements for every single thing. So make sure that you take the same principles of the math and just apply it to your own problems, okay? So as you guys can see, you should have already completed your data from the last class. You are collecting basically the mass of the object. I'm going to draw my pendulum over here. So here's my pendulum, right? Here's the ceiling. Here's the floor. Oh, I can't go off the paper. But you're going to measure this height. You're going to measure the height at the pendulum when it swings. So when it's up to the tape mark, you're going to measure this length, which is the height from the ceiling. So this is called your length right here. This part is going to be your H2. That's what I call it. This will be your H1. And H1 is when the pendulum is being dropped. So it's the height from where the pendulum is dropped to the floor. And this is your times, and then this is your mass. All right. So you should have already collected all this data from the last one. So the first thing I ask you to do is find your averages. The averages are pretty simple to find. It's pretty self-explanatory. You take T2 minus T1. You're going to add the sum of all of these, right? So you add these two and you add these two, and then you're going to divide by 3. That will get you your average. Once you have your average, that's the total time period it takes for the pendulum to swing. You guys get that? Yes? See? Okay. So the first part asks you to calculate potential energy of the weight at its initial position at the tape. So you have to solve it for 2 different positions. The first one's that the tape is 50 centimeters apart. The second one is 80 centimeters apart, right? So there's 2 different problems that we're trying to solve within there. So potential energy is going to equal mass times gravity times height. Okay. Should I use the calculator on the screen? Would that be more helpful for you guys so you can see as I plug in? Yeah? Calculator. How do I plug it in? Aha. No, not call. I should probably edit all of this out, shouldn't I? Oh my god. We're going rogue. I think my spelling's that bad. I'm not quite sure I know how to spell. All right. So we're going to come back here. Potential energy is mass times gravity times height. So for this one, right, I'm calculating what my potential energy is at this point. So I'm going to draw my pendulum up here again. So this is your equilibrium point when it's sitting like that. When it's up at your swing, at your top point, that's going to be H1. H1 is the one we're using to calculate this problem. So we're basically figuring out how high the pendulum is being dropped at, okay? So our mass for this project, for mine, is going to be 0.1. So I'm just going to plug in 0.1. My gravity, I'm just going to use 10. You can use 9.87 or 9.8. Those are all factors of gravity, but I'm just going to use 10 because it's a little faster for our purposes. And then my height. So I'm going to come back to my other page and look at my H1. So I'm looking at the height at which the pendulum was going to be dropped at, and mine was 0.13 meters. So basically 13.5 centimeters. So I'm going to come back here. It's 0.135 meters. So I'm just going to plug all that in. So I go 0.1 times 10, which should be 1. So if I times that by 0.135, it should just equal 0.135. So it's going to be the same value. Keep in mind that if your mass is not 0.1, that value will be different. The only reason why mine is 1 times 0.135 is because my mass is 0.1. So I go back here. So it's going to equal 1.35. And then what unit should I have on the end of that? What is energy always measured in? Joules. Cool. So this is going to be for my 50 centimeter drop. I'm just going to put 50 centimeter drop. or my 50 centimeter tape line. I'm going to do my 80 centimeter tape line on this side. So my 80 centimeter tape line, I'm doing the same exact problem. I'm going to say potential energy is equal to mass times gravity times height. So as you guys can see, mass and gravity are going to be the same exact thing. My height's the one that changes. So if I come back up on this one now, so this will be my H1 for the 80 centimeter drop, it's going to be 0.145, right? So I come back here and I say 0.145. Once I do all my math, I should get the same idea down here because it's going to be 0.1 times 10 is 1. So 1 times 0.145 is 0.145. So for my 80 centimeter drop, I have 0.145 joules. For my other drop, I have 0.135 joules. So which one's getting more energy if I swing my pendulum? Is it when it drops right here or if it drops at a higher? Yeah, because basically what you're saying is the higher you lift it up, the more potential energy you will have. The more energy is going to be generated at that bottom of the swing. All right, this is where it gets tricky, right? I'll use a different color. We'll mix it up. So kinetic energy and theoretical velocity. So kinetic energy, just the kinetic energy equation is this, is mv squared over 2. That's just kinetic energy, right? So if I wanted to calculate kinetic energy at that point, I could use that, right, equation. And I can also figure out that v. The v is going to stand for my theoretical velocity. So not the actual velocity, because actual velocity is distance over time. This is just theoretical. If everything was perfect, you didn't lose energy to friction or like any resistance, then it would be a perfect swing, and you could figure out that theoretical velocity should equal the actual velocity. All right. The other thing is when I have my mass like this, right? I have a point on the swing. So up here I have what kind of energy? At the top of the swing. Yeah, potential energy. At the bottom of the swing, what do I have? Kinetic. Okay, so I have kinetic energy. What else do I have at the bottom? Gravitational potential, correct. Yeah. So when it's just hanging there naturally, I already have potential energy on it. And remember, conservation of energy says energy is neither created or destroyed. It's just going to be transferred from one form to the other. So if I have potential energy here and I also have it at the bottom, the kinetic energy would not fully equal the potential energy. It's going to be kinetic energy plus potential, right? We do know, however, that at this point, right, so I can say potential energy, I'll make this potential energy 1, I'll make that potential energy 2. Potential energy 1, right, will equal kinetic energy plus potential energy 2. Does that make sense? Because if I have all this energy at the top, it's going to equal all the energy at the bottom. And the energy at the bottom is going to be a mix of the gravitational potential of that object and the kinetic that's generated from it. Okay? So we can just set them equal to each other because I know at the top I'm going to have this energy, and at the bottom those two will equal the same at the top. So I already figured out this one, right? PE1. So for 50 centimeters right here, this is my 50 centimeter side. I can say my potential energy 1 is already calculated from this problem right here. So I can say 0.135 joules is equal to kinetic energy, what we're solving for. Now, potential energy of the object hanging, what does that equal to? Close. So potential energy, what's the equation for that? It's from up here. There you go. So I'm going to say mass times gravity times height. And the height we're going to use is actually going to be this height right here. The height from the object just hanging at equilibrium. So I'm going to say it's going to be 0.1 times 10 times, I'm going to go back to my height up here. And my height from the floor at equilibrium, so H2 is what I called it, is going to be 0.13. So I'm going to go back here, and it's going to be 0.13. Okay? So I know that this potential energy should be 0.13 because 0.1 times 10 is 1. I know that I'm solving for kinetic energy, and I know that this is equal to 1.35 joules. So now how do I solve for KE? What do you think I do? If I'm just solving for this variable and I have these two values, yeah, you're just doing simple algebra at this point. So what should my answer be? Right? Should I double check it? .005. So that's going to be my kinetic energy at the bottom of the swing. Okay? Fair? Now we have to do the 80 centimeter side. So I'm going to do 80 centimeters over here. So I can say 80 centimeters. My potential energy is this now. So I'm going to say, okay, it's still going to be this equation. So I'm going to say 0.145 joules equal to kinetic energy plus my potential energy. Now this part is kind of easy. It's the potential energy equilibrium. No, because when we calculate the potential energy as it hangs there, it's going to stay the same. So I can use the same value as I did before. So it's going to be 0.13. Okay, so now I just solve simple algebra minus 113. Plug it in. So I go here, 0.145 minus 0.13. I have 0.015. Go back here. 0.015 is equal to kinetic energy. Are we all on the same page? So now I have my kinetic energy at both these spots. Right? Are we good on that? But ask for one other thing. Ask for what? Theoretical. Theoretical what? Theoretical velocity. Now I have to use this part. I'll change color so you guys can kind of see it. Is now I have to solve for that. And now I have KE already. It's right here. Do I have my mass? Now it's just simple algebra once again. So I'll do this first one right here. So this is for the velocity. I'm gonna say it's KE. So I have 0.005 equals mv squared over 2. So I'm going to times each side by 2. So I go back here and I go 0.005 times 2. 0.01. So I go 0.01 equals mv squared. My mass is what? So I'm going to divide each side by 0.1. So I'm going to go back here. I'm going to say divided by 0.1. Oh. Should be. Did I do that right? 0.01 divided by 0.1. Nope. Here we go. 0.1. So I'll keep working on this side. So it should be 0.1 equals v squared. So now all I have to do is square that, right? So we have 0.1, and now I have to do, where is it? Okay, hold on. Where's my square root? There we go. 0.1. Okay. There we go. So square root of 0.1 is 0.316. I'm going to round up, so I'm going to say 0.32. So if I come back to my little answer, my velocity, my theoretical velocity is 0.32 meters per second. That's my theoretical velocity for just the 50 centimeter one. that make sense? You understand how we got there? Essentially, all it is just simple algebra. Once you have the values, all you need to do is plug them in and solve for a variable. Okay? So if you're struggling with this concept, please come in for some help because the simple algebra stuff will not go away. It's just going to be a lot of equations, a lot of plugging in values and solving for a variable. So the same concept will be applied to this side. So I can go 0.15 or 0.015 equals mv squared over 2. So I'm going to times both sides by 2 to get rid of that. So it should be 0.03. So it should be 0.03 equals 0.1 v squared. So I'm going to divide both sides by 0.1. So I go here. 0.3 divided by 0.1 is 0.3. So it should be 0.3 equals v squared. So I now have to square root both sides to figure that out. So v should equal, if I go here, and I just square root that, 0.55. So I'm going to go back to my thing right here. So my theoretical velocity should be 0.55 meters per second. All right, at this point, we have both theoretical velocities. We have both energies for these ones. Now we need to move on to the fourth problem. Okay? Are we all on the same page at this point? If you go back and stop, do you have any questions? All right. Calculate the measured velocity of the weight and compare it with the theoretical velocity by using percent area. Okay, so you're going to calculate the measured velocity. Color. Okay, measured velocity. How do we figure out velocity normally? What's the standard equation for velocity? Perfect. Do we know our distance? Yeah, they were 50 centimeters apart. The other one was 80. Do we know how much time it took? Yeah, like if you guys did the problems right here, you should have this. That should be t. It should be t. So yeah, those are the t's for your problem. So if you go back here, v equals d over t. So my velocity of pendulum, this will be 50 centimeters side again. My distance is 0.5 meters. My time it took is 1.597. Cool. So if I go here, I can say 0.5 divided by 1.597 is 0.313. So I'm going to go right here. And my calculated velocity is 0.313 meters per second. Okay. Now what I want to do is compare it back to the velocity I got on that last one. So I'm going to go back up here. My theoretical velocity is 0.32. Was I pretty close? So my calculated velocity is this. My theoretical velocity of the VO dot V is what was it? Pretty close? How close was that? That's what it talks about right here, percent error. You want to figure out percent error because in any experiment in science, you want to try to get as accurate as possible. We like accurate things, right? You wouldn't like to go to the doctor's office and be like, oh, I have a 20% error. I'm only wrong about 20% of the time. That's no good. You'd be a little scared, hopefully. So what I want to do is I want to go to find my percent error. I go V measured minus V theoretical over V theoretical times it by 100. And I should have a percent error. So I'm going to go here. My measured is 0.313 minus 0.32 divided by 0.32. And I'm going to times that by 100. So even though it's negative, I'm just going to convert it to positive. So I had a 2% or 2.19% error. So I'm going to go back here. And it's going to be 2.19% air. Do you understand how we got there? So that's how you figure that out. So we're able now, I can fill up this top part. I'll let you guys figure out the 80 centimeter part. So I've already been through a lot of the math for the 80 centimeter. I'm going to leave the rest of it up to you guys to kind of figure out. It's the same process though, same math, same everything. So my potential energy, now I'm just going to fill in this table. I figured out potential energy of the 50 centimeter as 0.135. 0.135. My kinetic energy was 0.005. 0.005. My theoretical velocity was 0.32. My measured velocity was 0.313, and my percent air was 2.19. Okay.
Was it your theoretical one squared off with the meters per second?
This one?
Yeah.
Meters per second, yeah. Okay. The acceleration would be meters per second. I'm just finding the velocity of the swing at the bottom. So I had a 2% error, which means I was pretty accurate. What happens if your experiment had like a 20% error? It's kind of bad, right? What could that 20% error be accounted to?
Human error.
Human error? Maybe the timer wasn't timing correctly, or you guys didn't measure correctly?
Maybe, I don't know, could be the instructor.
Yeah, there's like a systematic error. Maybe what was happening when you dropped it? Maybe it hit a chair leg, or maybe it swiped against the board and you lost some of that energy due to friction. So, because this is not a really precise environment, we're kind of eyeballing the measurements, we're kind of timing with our phones. We're not very, very accurate. There is a chance that your percent error will be very, very high. And that's fine, as long as you can account for it. As long as you can say, oh, there was an error when we were reading our data. There was an error in collecting the measurements, or we lost some of our energy due to friction. So our kinetic energy turned into thermal energy. Okay? So this is one of the last parts I'll help you guys with. So you need to find period of the swing. You already have the period of the swing from up here. So you measured your average is going to be 1.597. So I'll go back down here. I'll say my actual time period is 1.597. That's what I actually measured, right? Now to measure your theoretical period, I'm going to say that the equation for that is going to be T. So the time period of the pendulum should be 2 pi square root of L over G. The reason why that is because you're kind of dealing with a semicircle or a half circle, because that's what the pendulum basically is. So you're going to have pi in that equation as well, right? So if I know L,
Sorry for reading that, it was stupid, but like.
you're fine.
Okay, so if you have the pi for doesn't include theory going circle if you fix it higher.
Yeah. So you're dealing with a semicircle. So with L though, so your radius is basically going to be called L, and that's going to be the length of the string from where you attach it to your desk to the mass itself. So L for us is right here is going to be 2.64 for mine. So I'm going to go back down here, and I'm going to say my L is 2.64. I'm going to say gravity is 10, so I'm going to square root that first. Let's try that. So 2.64 divided by 10, right? And then I'm going to square root it. So I have 0.514. So I'm going to round up just a little bit. So I'm going to say 2 pi times 0.514. So now I'm just going to plug this all in. So I'll do this one times 2 times pi equals 3.23. All right. So if I go back, this is the length of the full swing too, by the way. So that's the length of.
Is that why you didn't divide the pi, right?
Yeah. So I didn't go into full. So if I go back up here, if I look at the average between a full swing, which is T2, this is a full swing, and that's a half, right?
Okay.
So if I wanted to get my theoretical value, what I would do is go to this, and I would divide that by 2 to figure out what was the half swing. So 1.61 would be my half swing. So I'll go here, and I'll say this would also equal 1.61 seconds. Is that pretty close to my other half swing?
Yeah.
Because this one? Exactly. The other thing with this is because time period, does time period have height within there? But look at the equation. Does it have a height in there? It only has the length of the string. So why do you only have to perform this measurement calculation once for both set of trials? Because it's just length of the string. There's no correlation to the height. So when I ask you, why do you have to perform this calculation once? Because there's no height involved. Period should stay the same no matter what you drop it, because it doesn't have anything to do with the height. It's not related. Okay? So you can use this calculation for the trial at 50 centimeters and the trial at 80 centimeters, because this value will stay the same. You only have to perform the equation once. There's no correlation with the height. All right? It's then going to ask you too, what is your calculated period for each set of trials, and what is the percent error? So it's going to go through the same exact thing. You're going to say T measured minus T theoretical divided by T theoretical times 100. And that should equal a percent value of error, right? So our theoretical period, which we got was 1.61. Our measured for the first set was 1.5 what? 1.597. And then,
You always want us to go at least 1,000.
yeah. And then what you're going to do is see, it's going to ask you to do your theoretical set for the first one and then for the second one. Okay? So for my first one, I'm just going to go, my measured is 1.597 times 1.61 divided by 1.61 times 100. So I'll do that right here. No. So you go like this, minus 1.61. So that divided by 1.61. Oh, that wasn't right. 1.597 minus 1.61 equals a number. Divide that by 1.61. And then times that by 100. So we had a 0.8% error. All right, so we go back here. Our percent error for the first set is a 0.8% error. That's pretty good, right?
Yeah.
That's pretty like dead on. We did a pretty good math job. We did calculate our data really accurately. That doesn't mean that yours needs to be the same. So you can have a 10% error as long as you can account for why the period would change based on that. Okay? And then when it talks about first set, second set, this could be the 80 centimeter one. And that could be your 80 centimeter one. Okay?
So we just got plugged in.
Exactly. So it's asking this one will be your 50. Yeah. So it's not T1, T2. It's 50 centimeters and 80 centimeters. All right?
I think the only one I was hard was the first one.
Exactly. And then account for the percent error between your measured and theoretical. So it's asking you on that one, why do you have a percent error? What might have gone wrong within there? And again, that could be the timer was off. It could be there was friction. Maybe the person dropped it too soon after you started it. So you want to account for your percent error. And then calculate how long you would have to make a pendulum so that would have to have a period of 1 second. So that would be the same process right here. T equals 2 pi and then divided by L over G. You're solving for this one. So I'll actually erase the L and I'll make it a different color. So that way you know what you're solving for. You're solving for that. So then you would just set it up equal to 0 or 1, my bad. So you set the period equal to 1, you'd say 2 pi equal, that's my bad, 2 pi square root, you're looking for L, and then you know G is 10. And now it's just simple algebra again. Do you guys kind of see how you would solve that one? Because all you'd have to do now is basically you can get rid of these values to that side. And then once you get rid of those values, how do you get rid of square root? Square it. Cool. And now we'll get rid of your square root, which will leave you with L over 10. You times everything by 10. All right. Do you guys need me to go through that one? Would you like me to work through it? All right. Why not? Okay. So this whole equation, what we're going to do is we're going to go here. We'll divide by 2 pi. We'll divide by 2 pi. So 1 divided by 2 pi. So I go 1 divided by 2 pi. Oh, 1 divided by 2 times pi equals 0.16. So I'll go back here. This should be 0.16 equals L over 10. I can square that and then square this. So now I can go 0.16 squared equals 0.0256. So I go back to this. It's 0.0256 equals L over 10. I can times everything by 10. So it's basically just going to move my decimal point. So it's 0.256. So I have L equals 0.256. So basically it would have to be 25, almost 26 centimeters in order for it to have a period of 1 second. Yeah, that's if everything goes right. So in an ideal situation, you'd have to have a length of 1. Would it matter where you drop the pendulum? No. The energy would change, but the time period should change. Because it's independent. The last ones are just short answers. So based on your calculations and results, would it be more effective to have your pendulum with a period of 1 second swing for a higher height or a lower height? I'll let you guys kind of answer that short answer question. And then you are an engineer working on an amusement park. They have asked you to develop one of the fastest roller coasters in the US, but they also want it to be cost efficient. Therefore, you do not want to have to use a lot of energy to break the roller coaster. How would you develop this ride so that it's still easily accessible to the amusement park guests? I'll let you guys answer that as well. It's a short answer question. But everything else on the map should be presented to you guys. If you have questions on it, please come in. Again, these values are not the same as yours, so do not just copy the answers. Try to plug in your own values and figure them out. All right?